All right, so elevator stuff is all about forces. Okay, so in here, if you want to imagine that you are riding in an elevator, ignore my really terrible drawing here, but that's you in an elevator, and the elevator, let's see, the question said is going to go. So our elevator can basically do three things. We can be accelerating up, we can be at no acceleration or a constant velocity, or we can be accelerating downwards. Okay, and the person in the elevator has really only two forces acting on them at any given time, right? And those forces would be what? Gravity is one of them, and then the other force would be, so let me do gravity here. What's our second force acting on our person? The elevator acceleration is not a force. Okay, definitely is the outcome of it. But what's the force we're talking about here? Weight is gravity. That's going downward. So we already have that one. So mg, or the weight, included on there. One more force acting on that. Normal force. There we go. So then we've got our normal force, our F, and the floor pushing up. And now, depending on the question, they may refer to this as a normal force, the force of a floor, the force of a scale, lots of different options there. But those are basically the only two forces that our person has acting on. Okay. Now, here's the tricky part, and this is where I think these questions. Is my audio being terrible? It's a possibility. Let me see what I can do about that. It might just be a terrible thing. I can try another microphone if that helps. Is that any better? Yes, no, maybe. I'll solve it for maybe. Yeah, okay. All right, let me know if it craps out again, and I will see if I can make that work. For right now, I just moved the mic really ridiculously close to my face. Hopefully, it'll work a lot better. So basically, the key idea here, this normal force going on is what we feel as our weight. Okay, it is not how much we weigh, but this is what you feel with the weight. Okay, so if you are weightless, that just means that the normal force is equal to 0, and we don't have a force pushing upwards on us. It doesn't mean gravity is not pulling on you. It doesn't mean that you don't have weight. It means that the normal force pushing up is 0, not up. Okay. All right. That being said, I'm going to try switching microphones here for a second, since it's still apparently being a pain. So give me a second. I'm not going anywhere. Let's see if this works any better. Let's see now. I click here. I click settings. I open this up. Come on. There it is. And then we do that. All right, let's try this one. Is that any better? No, let's see, it's not working at all. A lot of nothing. Good, that's annoying. Test, mic, yeah. Crap. All right. Well, it's still showing up. This mic's working. Right. So we're going to try that with a new microphone. If it cuts out again, let me know. And I'll go to the third option, I guess, which is not ideal, but will work. Okay, so where were we here? We were talking about how if you are weightless, you have no normal force acting on you. Okay. Um, so, and again, this is where terminology comes into play, and terminology is really, really, really important for this. In there, if we are accelerating upwards in this case, that means that the normal force going up must be bigger than the weight going down, right? This is Newton's second law, F equals ma. The bigger force makes us accelerate in that direction. So this means that if we're accelerating upwards, we feel heavier. We feel like we weigh more than we do normal. If we have no acceleration, that means down and up are equal to each other, and we feel normal, right? We are not heavier or lighter in that. Does that make sense? Okay. And then finally, if we're accelerating downward, that means the down force is bigger than the normal force, which means you feel lighter. Okay. Um, and that's really all I mean, we could do practice problems and stuff like this. This is the gist of the um, acceleration and forces sort of stuff. So if they gave me the acceleration upwards, let me change colors here and we'll knock off that part of it. So in the example that the chat gave, we have an acceleration 1.3 meters per second squared going up. Do we know the mass of the person or anything like that? Okay. So basically, I'm waiting for a to see if we're going to get numbers or if we're just going to say, hey, the sum of forces must be m times a. So this must be we're accelerating upwards. That's the normal force. Do I need it? Yeah, I do need that. Minus the weight pulling down, minus gravity pulling down, must equal. Oh, we can do it in terms of g. I guess that works. So the normal force must be equal to 1.3 m. I'm going to use g as 10. So that's 10 m. The normal force must be equal to 11.3 times their mass, whatever that works out to be in there. But that's the deal for it. And they may give the weight instead or other stuff like that. But that's the gist of how you would go about solving if they asked you to do a how much does this person feel like they weigh or what happens to their weight and stuff like that. I'm going to expect this year's exam wise, you'll see a lot more of the do you feel heavier, lighter, or the same, and explain why sort of questions. But the math is just the second law. It's just F equals ma in there, and then just make sure we're getting the forces put in the right order. So because we're accelerating up, upward force comes first. If we were accelerating down, we just flip the order of those two things. Okay. Any other questions about elevator stuff, or are we ready to jump into our 2019 FRQ? Okay. Let's dive into some of these. All right, so this is last year's free response questions, and I would say they're a really good model for what we're going to be looking at for potentially this year's. Remember, this year we only have 2 questions on the exam. It's a qual quant and it's a paragraph length response one. So this is not a bad example of something you could see. It's actually looking pretty reasonable here. So this is the 7.13-minute question on here. So let's knock it out. We're given 2 identical blocks, block 1 and block 2, and we're going to place them on a horizontal surface at points A and E as shown. The surface is frictionless, except for the region between C and D, where it is rough. So we have friction in that region, but nowhere on the track. Beginning at time TA, block 1 is with a constant horizontal force from point A to point B by a plunger. When it reaches point B, it loses contact and continues to the right along the horizontal surface. It collides, sticks, that could be important, collides with and sticks to block 2. Afterwards, it moves all the way through. Okay. So, looking at this question, a couple things pop up as far as topics here that we could see. We're looking at them saying we've got a block pushed with a constant force. So that could mean forces. That could mean energy. Something like work equals force times distance could show up in there. And then it mentions that they collide. So I'm looking at momentum being another possible topic here. Okay. So for this question, we're looking at forces, maybe energy, and momentum on here. All right. On the axis below, sketch the speed of the center of mass. Key part here of the 2-block system as a function of time from TA until the blocks pass point F at time TF. And we're given all the times there. All right. So we are looking at those 2 blocks as a complete system. Total one object, or one combined sort of thing. Remember, this is the key idea for this question here, is external forces lead to changes in motion. If we do not have an external force, the center of this entire system will not change how it is moving. If we do have an outside force, then we will see a change in motion of that object. Does that make sense? All right. So with that, why don't you guys think for a little bit? Where are the regions on this graph where we will see an external force? Where on this TA, TB, TC, et cetera, do we actually have an external outside force acting on our 2 blocks? All right. So there are 2 places in this scenario where we have external forces acting on our blocks. There's an external force caused by the plunger, And there's external force caused by friction. Everything else that happens, there are either no forces on the block, or it's an internal force, like when the blocks collide together. Okay? So what that means is my speed of the entire system, the two-block system, will increase when the plunger is pushing on it, decrease when I have friction, and then nothing else will change at any other point on this track. So the answer for this, we're looking at something like, and again, this is scale, so you can use your own scaling if you want to. Something like this. Okay. Here we have a constant force. Whoa, apparently I'm clicking stuff. Why am I? Okay. Constant force and constant acceleration for that chunk. B to C, no forces. We shouldn't accelerate at all. C to D, we have friction. So it's not a constant negative acceleration there. We have the force working backwards, taking away some more speed. And the rest of it, completely flat. Horizontal for that. All right, questions on that part? Are we good to move on? Because if we don't get this part, the rest of the question gets a little iffy. So, on there. Okay. If this was this year's AP question, this first part is actually worth 5 points, which is kind of ridiculous considering all we did was draw a graph and they gave us the majority of the points for this question. But here's how it breaks down. We would get 1 point for the first chunk. The force from the plunger gives us a constant acceleration because the force is constant. You get 1 point for horizontal and non-zero. You get 1 point for a negative constant slope between C and D. You get 1 point for one horizontal line that continues onwards from D through F. This has to be a different value. Than TVTC, so it's going to slow down a bit after that. And then we have to do something like the last one, would just be it's continuous. We don't have any breaks or gaps or anything crazy going on. It's all just a nice constant, continuous. Fine. Okay, ready to move on? Okay. All right. Let's go on to the second part. C to D. Wow, is my audio really lagging here? Interesting. Okay. All right. Very interesting. This is still going. Okay. Huh. Weird. All right. So yeah, I'm not getting a response from the chat. So we're going to kind of just kind of keep pushing forward here, and we'll see what happens. For those of you who are still here, if you can let me know that you can hear me and I'm actually doing stuff, let me know. But I'm going to go through and try to knock off the next couple of these on there. All right. Part B. I'm cutting off a little. I'm still here. Okay. I can't tell you how paranoid I am about my internet just deciding to chop off and me just sit here talking and no one else is responding. So, all right. Part B. The plungers return to its original position. We take the blocks away. We now put a sphere in there. Okay. Sphere loses contact, goes through, blah, 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 gets pushed off at point B, continues moving along. Which interval does the sphere's angular momentum about its center of mass change? All right, so it's a sphere. What do spheres do that blocks cannot? They can roll. Now, in order to roll, we need to change our reasoning a little bit here. An external, let's spell it right, external torque changes our rotation. Okay, remember, a torque is force times radius that is perpendicular to each other. All right, so if we go back to our two options here, where we have the plunger as an external force and the friction as an external force, which one of those two, or both of them, can make a torque on our ball? So which one of these can make a torque on our ball? Or none of them. The friction, yeah, the friction does. If this is my ball here, friction would act at the bottom. So yeah, there's my radius, there's my force. So yeah, definitely C to D can make a torque. Can the plunger? What the plunger option here? All right, so the plunger cannot. And here's why. The plunger is going to put a force sideways on it, which happens to be the same direction as the radius. Oh, don't click that. Go away. Oh, please stop. Because it's perpendicular to the radius now, we don't have another option because it's parallel to the radius. Stop grabbing the text. Sure. Done. Go away. Done. Go away. Grab that. Okay. So because it's parallel, we don't get a torque. Here we have the force perpendicular. So we get so the only place on here where we can have a torque or change in angular momentum would be between C and D. And if we want to briefly explain our reasoning, we'd be looking at something like the external part. And there's a possible paragraph or short explanation. I wouldn't call it a paragraph yet, but explaining the reasoning and stuff like that. All right. How is the friction perpendicular to the radius? Okay, so if we're looking at this, let me make another call here. Get some space. All right, so if we have our sphere right here, the radius points towards the center. Obviously, it's a radius sort of thing, but the friction only acts on the bottom part, acts where the sphere touches the ground. So friction can only act at this one point, and it's either going to pull it, let's see, in this case, it's going to try to slow it down. It's going to pull it to the left. Okay, so that's the force of friction that gets applied, pointing to the left. The radius going upwards. Stop. I gotta watch my palm. Makes a 90-degree angle there. So that is our perpendicular force and radius sort of example. Okay, compare that with the plunger. The plunger pushes on the ball and pushes on the center of the ball. So the force from the plunger is going to be pushing this way, which happens to be exactly in line with our radius. So those are parallel to each other, whereas the friction one is perpendicular. So the friction one, because there's a 90-degree angle between the force and the radius, we get a torque, and the plunger one does not have it. So that does not make a torque. Does that help? Yep, no problem. All right, let's see now. Let's see if I can just get this all on one screen so I can download it easier here. That'll work enough, I guess. All right, next question. So that was question 1. 13 minutes in there, and we did it in about 20 or so. Not bad. Not bad. We took the time to explain all the stuff there on there. Remember, you guys have a 15-minute question and a 25-minute question. So keep that in mind for when you're going through your stuff as well. All right, number 2. This is your qual quant. This is your qualitative quantitative stuff. Do stuff without using math and equations, and then do the same thing, but now use equations and tell me how they're the same. So in this case, we're doing a qualitative quantitative with 2 blocks on a table. So we're looking at how the relative masses of the blocks on the table affect the acceleration of the blocks. So we're told block A is on the table. There is no friction. That's good to know. So we can say there is 0 friction here between the block and the table. Whereas block B is free to fall. Okay, pulley has no mass and no friction. Good to know. That part means saying the pulley is no mass. I don't have to worry about any sort of rotation stuff. or torques or anything like that, which is wonderful. We can treat this as one complete system, one sort of thing. I would let you go. Okay, so a single line. We're going to say, hey, what happens if block A gets much bigger than block B? So if block A is our big heavy one and block B is our really light one, what's going to happen to our acceleration? Small. Yeah, actually, very, very small is a good answer for this. This acceleration will be very small. I'll say very small. You could also say this could be close to zero, much less than G. Lots of options there. We have to say that really is really small acceleration. Hey, now, why? Why is that very small? The mass of A is greater than B. Okay, true. A is definitely bigger than B, but why does that mean the acceleration has to be small? F equals ma. Okay, yeah. Now we're getting into stuff we're going to talk a little bit. Now, the trick for this part is they do want us to do this without using any equations. So we have to say F equals ma without using the equation F equals ma. Does that make sense? So you can say, you can talk forces like that. Or you could say, there's another option. Okay? So you can talk about it in terms of forces. You can talk about it in terms of inertia, stuff like that. But the big idea here is we're not going to use any equations. We're not going to derive an equation for the acceleration of the whole thing. We're simply going to say, yeah, it's not going to go very much. That, by the way, is worth a very nice 2 points if you're keeping score on your AP rubric. You basically get a point for coming to the good conclusion there and some correct justification. Right, some correct reasoning going on. All right, double I. Now we switch it. Block A is less than block B. How does that change our acceleration? Well, if we grab this and flip the logic here, our acceleration, it's got to be is much larger than in A. And what's part I? Yep, that's good. So we basically have to say that it's higher. In fact, we could pretty much say, oops, go back to editing this. Come on, click the text. It'll be really close to 10 meters per second squared. Okay, how close? Super duper close. Okay, because reasoning time, why will it be so much closer to 10 meters per second squared? Well, now it's basically falling. Okay. Again, you could do F equals MA logic and stuff like that. But in this case, if you imagine block A being nothing, then block B is just going to fall through that. So this part, unfortunately, only gets you 1 point because they kind of, if you get part A, you can get part I, you can get double I, because it's just flipping the script on that. All right, questions on this chunk? Okay. Next part. Now we have to suppose neither block is much bigger than the other. So now we have two roughly identical blocks, but they are not necessarily equal. The dots below represent A and B as indicated by the labels. Draw and label the forces, not the components exerted on the block. Okay. I'm going to cheat for a second here. Just paste in the diagram we were working on before. So we've got that to work off of. So let's put that off to the side here. That's the picture we're working off of for our table. Let's draw some free body diagrams. So let's start with A, because that's a good one to start with. How many forces are there acting on block A? So I have A has normal force and T from the rope. True. Normal force goes up. Tension from the rope going sideways. And gravity. There we go. And of course, we have gravity pulling downwards. Anything else for A? Okay, yeah, friction would be the other one. They specifically tell us in the question above that there was no friction between A and the table. But yeah, that would be the other one you could possibly have here. But they specifically said in this question that there was no friction. So yeah, that was the one I wanted you guys to come up with. And then we can say, no, it doesn't matter in there. So there could be friction, but not in this case. So A is good to go. We got everything in there. B. Gravity going down. Yep, nice easy one here. And tension going up. Okay, now here's the question. Are those two tensions the same? Or do I need to put a T1 and a T2 on them? Yes, question. I like it. All right, so in this case, yes, the tensions are the same. And why are they the same? They are the same because this pulley has no mass. Yep. If that question said we had a heavy pulley or a big pulley or anything like that, then the tensions would not be equal to each other. But in this case, they are. So this is good. Okay. So just keep that in mind. In this case, the pulley doesn't matter at all. It's just changing the direction of the forces. If we were doing this as a rotational question, where we hit stuff with moments of inertia and stuff like that with that pulley, then we would not be able to say that T from block A and T from block B would be the same. But in this case, they are the same tension, and those diagrams are correct. All right. Can't see. There we go. All right. So part C now wants us to do the math part of this. We've done the qualitative. We've done the number stuff on that. Oh, actually, let me go back for a second because points are important. With this, this free body diagram gets you a total of 3 points. You get 1 point for block A stuff. You get 1 point for block B stuff. And then you get 1 point for the tensions being the same. Okay. Actually, scratch that. Let me read this again now. You get 1 point for doing correct gravities, 1 point for the normal force, so 1 point for having gravities on there that are labeled appropriately, and then you get 1 point for tensions. So nice little 3-point thing. If they give you a chance to draw a free body diagram, do it, even if you don't know anything else about the question, because it's almost always super easy points for very little effort. All right, yeah, part C. Part C asks us to derive an equation. So now we're doing some math from the acceleration of the blocks in terms of MA, MB, and physical constants as appropriate. Yeah, okay. So what we're going to do is we're going to look at blocks A, B, and we want a total equation for this. Now, I believe I said this on a bunch of streams already, but there are 2 ways to do this question. We can do it with block A and block B as separate things, or we can do it as one complete system. Which one do you guys want to tackle first? All right, so let's do it as individual stuff. We're going to do, for the both cases, it works out to be about the same thing. F equals MA. Let's do this with block A, and then we'll do F equals MA for block B. Block A, the only force making it accelerate is tension. And for block B, it must be the difference between the weight of the block and the tension must equal MBG. Okay, so we found our net forces, our unbalanced ones, and can just step through, write out some Newton's laws equations for them. Laggy. Now, the only problem is this answer has to be in terms of MA, MB, and physical constants. I'm not allowed to have any sort of tension in my final answer. So I have to take this tension and plug it in to my other equation. Oops, that should be an A. Thank you, whoever wrote that in the chat. And then we can go through and just solve for A here. So MBG equals MA plus MB all times A. And there's our answer. If you want to do this as a system, you'll end up with the same exact answer, but it's a little bit quicker. In there, if I look at the whole thing as one entire system, what we can say is the sum of the forces of the system must equal MA. The only outside force of the system is gravity. Tension is internal. It's included in my big loopy thing. So we can say mvg equals mass must be the mass of the entire system. So that's the mass of the 2 blocks times A. And then finally we get to A equals mvg over ma plus mb. It's the same exact thing, just with less math to go with it. So either way you want to do it, that is how you go about solving part C. All right. Questions on that part? Okay. Part D then. Consider what we just did. In part A double I, if the mass of A is much less than the mass of B, does our equation support that? Well, I guess the short answer is yes, it does, because we've done everything on it so far. But now, why does it support it? Well, briefly explain our reasoning. Here's my reasoning. If I make A equal to 0, much less than B, I get mass of B times G over mass of B. Those cancel out, and I get G as my answer. So basically, I plug 0 in for A, and I get G. And that's exactly what we said should happen. Way back up here, it's really close to G. That gets you a grand total of 1 point. So, yes, with right reasoning in there. Or, I mean, you could also say, let's say we screwed up part A double I, and we say, no, it doesn't, because our math shows that it should equal 10, and our answer was something totally different. That's okay too. You still get points for that, because they're not going to penalize you twice for the same mistake. Not all right. And now the last part. The last part of this question, looking at what happens with a bigger pulley, a more massive pulley. And what has to happen here? All right, so we're taking this situation right here, so normal. We have mg going down, T1 going up. This is a light pulley. Now we're going to replace it with a heavy pulley. That heavy pulley now will have T2, some other tension going on there, going to our block A. So something like that. So now we're asked to say we're going to be accelerating. We have T2, how do the two tensions compare to each other? All right. So, well, what's going to happen here? The big idea here is that now this force, this massive weight of B, is no longer just pulling back in along the line. It is also cause this heavy pulley to rotate, which means that it's going to be harder to make it accelerate. The acceleration here must be less than the acceleration of the heavy pulley. Does that make sense? And because the acceleration, you don't get it. Okay. So let's go back a bit here. With the light, okay, it was pretty easy. We had two forces acting on our object, and we said that the acceleration depended on the mass of the total block and the mass of the, or the weight of the block B. Okay. This was with the light pulley. We didn't care about it. With the heavy pulley, we now have to look at three different things. We have to look at block A having a tension. We've got to look at block B having gravity and a tension. I'm going to call it TA and TB for a second here. And the pulley now has two tensions on it. Those tensions are not equal to each other. TA cannot equal TB. If that was true, then the pulley would not rotate and we wouldn't move anywhere. Okay. So if we're looking at Newton's laws here, we can say some of the forces on A must equal MA times acceleration. TA equals MA, like that. The forces on the pulley, actually, I can't do pulley. Forces on B equals MBG minus TB equals MBA. They all have to have the same acceleration. So all these things accelerate the same way. So I'm at two blocks, nothing fancy so much here. But now I look at the pulley, we have to look at torques. Is I alpha. Okay. This would be TAR minus TBR. Crap, doing the wrong way. TBR. In there. Basically, what's going to happen here is instead of all of this force, actually, yeah, because the pulley itself has to have some force going on it. I just thought of a much better way to explain it. So I'm going to erase everything I just did, simply because I can. This would be the derivation you have to go through if they wanted you to actually derive this. We don't need to derive, we just need to prove it. So let me go back a step here. I'm going to go all the way back to this part here, where we looked at the system. Okay, where we said we can take the entire, come on, grab the pen, the entire block system, everything in that orange circle, and count it as one object and do F equals MA. Well, with the heavy one, now I have an additional mass to do here. So this is with the heavy pulley. I have the same downward force. But now it needs to accelerate the mass of A, the mass of B, and the mass of the pulley, because the mass of the pulley is super heavy now. We just added in a brand new term. Because of that, this A2 must always be less than our A1. So because we had our pulley added in there, we're making our acceleration smaller because we are increasing the mass of our entire system. Is that a better way to look at it? Okay. So now let's get back to our answer to this now. Getting rid of free body diagrams and stuff like that. Let's look at just block B again now. It has gravity going down, and it's got some tension going up. For block B, the difference between them has to be the net force, which is related to our acceleration. Or solving another way, it must be MBA minus MBG. So if I look at case 1, I know this is bigger, which means my tension needs to be smaller. In case 2, a smaller acceleration means that these two forces tension and weight almost equal to each other, or at least closer to it. So because the tension is closer to the weight, that means it's got to be a bigger value. So we should have the T2 is bigger than T1 box checked here. All right. And explaining the reasoning for this. We can do a couple different things. Okay, but I think I want to word it something like that, and I would throw in the math equations to show it as well. Insert when appropriate, stuff like that. But it's a lot harder to type out these than it is to write them by hand. So here's our kind of overview, sort of stuff like that. Does that make sense? Have a great rest of the day, guys, and I hope to see you again soon. Take care.